Hi friends, this video contains the topics of M1 of Regulation 2019. It is especially made for Anna University students and also related to JNTU syllabus. If you want to pass the test in first attempt and also to score good marks, then you please watch this video. I'm sure it will help you a lot. Now let's enter into the syllabus, which includes matrices, functions of several variables, integral calculus, multiple integrals, and differential equations. First unit is matrices. Now I am going to discuss the topics of matrices. Here, these are the basic terms we are going to see in the problems. First one is symmetric matrix. A matrix is called as symmetric matrix when A is equals to A transpose. When this condition satisfies, then that particular matrix A would be called as symmetric matrix. Singular matrix. For this one, determinant of A should be is equals to 0. If det A is equals to 0, then matrix A would be called as singular matrix. For the non-singular matrix, determinant of A is not is equals to 0. If this condition satisfies, then it would be called as non-singular matrix. Orthogonal matrix. For this, A into A transpose is equals to A transpose into A is equals to identity matrix. If this condition satisfies, then the matrix A would be called as orthogonal matrix. These are the topics of matrices. First one is characteristic equation. Here we need to find out characteristic equation for a given matrix, and the given matrix would be of 2 by 2 or 3 by 3 matrix. Here we have two methods. First one is we have direct formula, that is determinant of A minus lambda I is equals to 0. This is the characteristic equation formula. Here A is the given matrix and I is the identity matrix and lambda is the eigenvalue. For example, we take 1, 2, 4, 5 is a given matrix of 2 by 2 order. Then how to find out the characteristic equation means we need to just substitute this A in this equation and corresponding 2 by 2 identity matrix, that is 1, 0, 0, 1. So we need to substitute this A and I in this equation and simplify, and you will get the characteristic equation in terms of lambda. For example, after substituting and calculating this, we might get lambda cube plus 2 lambda square plus 5 is equals to 0. So I am just taking this as an example. So this is the characteristic equation in terms of lambda. And one more method we have for 2 by 2 matrices. 2 by 2 matrix, we have direct formula of characteristic equation, that is lambda square minus s1 lambda plus s2 is equals to 0. Here we will get alternate plus and minus signs. First plus positive sign and negative and again positive sign, where S1 is equals to sum of main diagonal elements. Sum of main diagonal elements. Here, if you take matrix 1, 2, 4, 5, the main diagonal elements here are 1 and 5. So 1 plus 5 is the S1 here, and S2 is nothing but, here S2 is determinant of A. So for S2 we need to find out the determinant of this matrix. We'll get some value. So just substitute S1 and S2 in this characteristic equation. We'll get directly the required characteristic equation. If the matrix is of 3 by 3 order, then this formula will change. For 3 by 3 matrix, we have lambda cube minus s1 lambda square plus s2 lambda minus S3 is equals to 0. I told you alternative positive and negative sign will occur in this characteristic equation is equals to 0. This is for 3 by 3 matrix, and where S1 is the sum of the main diagonal elements as before, and S2 is the sum of the minors of main diagonal elements. I will explain you this one with an example afterwards. And S3 is the determinant of A. And first find out S1, S2 and S3. Just substitute them in this equation. We'll get direct characteristic equation. And one more term here we see characteristic polynomial. This one is determinant of A minus lambda I. So here the difference between characteristic equation and characteristic polynomial is, here we'll get is equals to 0 and here we don't get any is equals to 0. So equation means we'll get compulsorily is equals to 0. For characteristic polynomial we don't get that term equal to 0. So this is the basic difference between characteristic equation and characteristic polynomial. Second topic is eigenvalues and eigenvectors. These are related to characteristic equation. For example, if we get a characteristic equation for a given matrix as lambda square minus 5 lambda plus 6 is equals to 0. And the roots of this equation are lambda is equals to 2 and 3. So these are the eigenvalues. Now we got 2 eigenvalues, so we'll get corresponding 2 eigenvectors. For this one eigenvalue we'll get one eigenvector, and for this eigenvalue we'll get corresponding eigenvector. Most probably we'll get 2 or 3 eigenvalues and corresponding 2 eigenvectors and corresponding 3 eigenvectors. And the third one is properties of eigenvalues and eigenvectors. Here we have some properties of eigenvalues and eigenvectors, and depending on those properties we have few problems. We'll discuss them later. Next topic is Cayley-Hamilton theorem. This theorem states that every square matrix satisfies its own characteristic equation. That means if you take a square matrix A and it has the characteristic equation, for example, consider it as lambda square plus 2 lambda minus 1 is equals to 0. According to this theorem, this A matrix satisfies this characteristic equation. That means if you substitute this matrix A in this characteristic equation, and we'll get A square plus 2A minus 1 into identity matrix. It gives you 0. Satisfies means it gives you 0. Why we multiply with this identity matrix means, here we have A square is a matrix, 2A is also a matrix. To compute this calculation part, we need to multiply this scalar 1 with identity matrix, because to compute this and to get 0. Uses of this Cayley-Hamilton theorem is, we can find out the powers of matrix A. That means you can find out A square, A cube, A power 4 like that, and inverse of matrix. That means A inverse you can find out using this Cayley-Hamilton theorem. Till now, I've finished first 4 topics, that is up to Cayley-Hamilton theorem. In next videos, I will give you an example problems for each and every topic. Now, I want to continue with the fifth topic, that is diagonalization of matrices, and along with the sixth topic. Now we'll go to the fifth topic, that is diagonalization of matrices. Here we need to convert the given matrix into diagonalized form. Diagonalized form means where we have only diagonalized elements and rest of the elements will be 0. This is the diagonalized form. So for the given matrix, we need to convert this into diagonalized matrix. Here we have two methods. First one is similarity transformation method and second one is orthogonal transformation method. But how do we select these methods means it depends on the given matrix. If the given matrix is of non-symmetric, the condition here is if the given matrix is non-symmetric matrix, that is A is not is equals to A transpose, then we can apply this similarity transformation method. And if the matrix is of real symmetry, that is A is equals to A transpose, we can apply this method, orthogonal transformation method. And in similar transformation method, we have one more condition, that is eigenvalues should be distinct. Then only we can diagonalize the given matrix into diagonalized form. Otherwise, we cannot. And the steps here we need to follow is first we need to find out the characteristic equation for the given matrix, and after that we need to calculate the eigenvalues by solving this characteristic equation, and again we need to find out the corresponding eigenvectors, and using these eigenvectors we need to form a model matrix P. I will explain you all these with the example problem later. And after getting this form model matrix P, then we need to calculate P inverse and product of A and P. So these terms we need to calculate. And after that, to diagonalized matrix, we need to multiply P inverse with the AP. So this is how we can calculate diagonalized matrix in similar transformation method. And when we go to orthogonal transformation method, these are the steps we need to follow. First, we need to find out the characteristic equation for the given matrix, and again we need to find out the eigenvalues and again eigenvectors. Here we need to form a normalized matrix N. So this is the basic difference between similar transformation and orthogonal transformation. Here we can see P in similar transformation method, but in this orthogonal transformation we can see the N term, that is normalized matrix. And again here we need to find out the N transpose and AN, and to find out diagonalized matrix we need to calculate this NT into AN. So this is how we can get diagonalized matrix in orthogonal transformation method. In first method we have an advantage. Before going to this point, I would like to explain about the similar matrices. If A and B are two similar matrices, then we need to remember that determinant of A would be equal to determinant of B, and eigenvalues and eigenvectors of matrix A is equal to eigenvalue and eigenvectors of B. And also we need to remember every matrix is similar to itself, that is A is equals to I inverse A into I. So this is applied in this first method, that is D is equals to P inverse AP. That's why it is called as similar transformation method. In this case, A and D are two similar matrices and the eigenvalues of A and D are the same. So here the advantage is these eigenvalues of A would appear in the diagonalized matrix. That means this D11 and D22 are nothing but the eigenvalues of matrix A. Hence, we can confirm that the obtained diagonalized matrix is correct when it has the eigenvalues of matrix A as D11 and D22. Now the sixth topic is reduction of quadratic form to canonical form by orthogonal transformation. Before going to this main topic, I want to discuss few subtopics. That is, if they give a quadratic form, then we need to convert that into matrix form. And if they give a symmetric matrix form, then we need to convert that into quadratic form. Quadratic form is nothing but a homogeneous polynomial of second degree, and this is the example. If you observe three variables for x1, x2 and x3, the power here is 2, so the degree is 2. And for the another three variables also, the power is 1 plus 1, 2. The total power is 2 and the degree is 2. So this is the example for homogeneous polynomial of second degree. If they give the form quadratic form, then we need to convert that into matrix form by using this formula directly. For example, let's take the same example 5x1 square, and how to convert that into matrix form means it is coefficient of x1 square, that is nothing but 5, and half of coefficient of x1 x2, that is half into 2, and half of coefficient of x1 x3, that is minus 7 by 2, and half of coefficient of x2 x1, and that is 2 by 2. Quotient of x2 square is 2. Half of quotient of x2 x3, that is minus 1 by 2. And half of quotient of x3 x1, that is minus 7 by 2. Half of quotient of x3 x2, that is minus 1 by 2. Quotient of x3 square is minus 3. So this is the matrix form for the given quadratic form. And if we have given a symmetric matrix form, then how to convert that into quadratic form means by using this direct formula. And this is the example, like the elements, these are a11, a12, a13, and this is the quadratic form formula, that is a11 x1 square and plus a22 x2 square. So what we need to do is we need to just substitute these elements into the formula directly. So we will get the quadratic form directly. Now, reduction of quadratic form to canonical form. Canonical form is also called as sum of squares of unknowns. For example, you see here the quadratic form. The question will be like this, and we need to convert that into canonical form, which is the sum of squares of unknowns. Here, y1, y2, and y3 are the unknowns, and we have two methods to solve this. First one is non-singular linear transformation, and the second one is orthogonal transformation. Mostly we have problems regarding this orthogonal transformations. So we see this method how to do. So this is the quadratic form, x prime ax will be given, and we need to convert that into canonical form, that is y prime dy. Here x prime y prime are the x transpose or y transpose, and where y is equals to column matrix y1, y2, y3. These are the steps we need to follow. First we need to write a matrix form for the given quadratic form. Like before, I told you how to write the matrix form from the given quadratic form. So this formula we need to use, and first we need to convert that into matrix form. After that, we need to find out the characteristic equation, again eigenvalues, eigenvectors, and we need to form a normalized matrix. After that, we need to calculate n transpose in and an. Lastly, diagonalized matrix as nt into an. So until this, we followed the steps which we used in the diagonalization of a matrix using orthogonal transformation. And after that, we need to write the direct canonical form as y prime dy. we need to put this diagonalization form here, and y as y1 y2 y3, it's a column matrix, and y prime as row matrix. So we'll get canonical form like this. This is the example. Last topic in this unit is nature of the quadratic form. Here we discuss about index of the quadratic form and signature of the quadratic form, and how the quadratic form, is it a positive definite or a negative definite. I have a table for this. I will discuss. First, index of the quadratic form. This is the number of positive square terms in the canonical form, and it is denoted by S. So this is the canonical form, and how many number of positive square terms are there? Here only one positive square term is there. So here index is the 1. And signature of the quadratic form. This is the difference between the number of positive and negative square terms in the canonical form. So here we have two positive terms and one negative term. That means 2 minus 1 is equals to 1. That is, this 1 is the signature of the quadratic form, this form. We have nature of the quadratic form using eigenvalues. So this is the basic table we need to follow. So first we need to find out the eigenvalues of A given matrix. If all the eigenvalues are positive, then we can say that the quadratic form is a positive definite. If all are negative values, we can say that negative definite. And if at least one eigenvalue is 0 and all others are positive, then we can say that positive semi-definite. And if one eigenvalue is if one eigenvalue is 0 and all other are negative, then we can say that negative semi-definite. And if eigenvalues are positive and negative both, then we can say that quadratic form is indefinite. So this is the table using eigenvalues, and we have one more, nature of quadratic form through principal minus of A. So this is the table we need to follow. This is also same like before eigenvalues. If see here, principal minus of A, those are the D1, D2, D3. I will explain you this later with the example problem. So if all are positive, then we can say that positive definite. So this is the same thing which we have followed for the eigenvalues.